Hello and welcome to a quick overview of work and energy. So here's the deal. What is work? Work is one of the concepts in physics that really has a definition that doesn't work with what we think of for regular life. So you go to work, you do effort, whatever, but in physics land, we're going to say that work is the application of a force, and we're going to apply that force over some distance, traveling through some distance. So if my car stops working and I get out and I push it down the road, I can apply a force and that will make my car move. But I'm going to say that the work that I do will be applying that force over some distance. So if I apply this force of, I don't know, 10 newtons, no, I guess I'd need more than that to move my car, 700 newtons of force times 50 meters of distance, that would be 35,000 joules of work that I did in moving my car. So the work done on an object by a constant force is defined as the product of the magnitude of the displacement times the component of the force parallel to the displacement. Work equals FD cosine theta. So I guess we could look at this person pushing the car and say, well, gee, some of their force is in the positive x-axis, but it looks like maybe they're pushing down. So if some of their force is in the negative y-axis, well, that's maybe not the smartest thing this person ever did, but some of their force is in the negative y-axis, then that force isn't contributing to the car moving. So what we have to do is take cosine theta, the angle between the force and the displacement of the car. Since the car is only allowed to move in the positive x-axis, and some of the force is in the positive x and some's in the negative y, then we would have to make sure that we're just using the component of the force that is in the positive x. Alright, so work equals force times displacement. Force is mass times acceleration. Acceleration is change in velocity over the change in time. Velocity is the change in displacement over the change in time. So what the heck are the units for work? It could be newtons times, force is in newtons, so it could be newtons times meters, or we could say mass times acceleration, so kilograms times meters per second squared times meters, or maybe kilograms times meters squared per second squared. It gets pretty wild after a little while, but what we're going to say is that the unit for work is joules, and joules is a collection of any of those things that you see above us here. So joules is newtons times meters. Joules is also kilograms times meters per second squared times meters, or if we multiply that through, kilograms times meters squared per second squared. All of those things come out to the same thing, which is joules. Talked briefly about the tension force. The tension force is the force that is directed in the positive axis that opposes if you pull down. There's another force pulling back up. That's the tension in the string. Turns out if you manipulate something with a bunch of pulleys, what you could have is a situation like this. This wouldn't be very safe, but you could do this where somebody's sitting in a box, lifting themselves up. The pulleys are providing 3 times the tension force. All 3 tensions are opposing the weight. If this person wants to hold himself motionless and he and the box weigh 1,000 newtons, then he only has to provide 333.3 newtons of force to hold himself still. And then to lift himself at constant velocity, then he would have to provide a force of 333 newtons times 10 meters 3,330 joules of work he would be doing pulling the thing. Actually, not true. You know what the truth is? The truth is that in order to lift himself up, if he and the box weigh 1,000 newtons, then the work he's doing is going to be lifting his mass, his and the box's mass, times gravity, so that's 1,000 newtons, times 10 meters, and so he'd be doing 10,000 joules of work. The way this pulley is arranged, in order for him to lift himself through a height of 10 meters, he would have to pull for approximately 30 meters. So he'd still be doing the 10,000 joules of work, but he wouldn't have to ever be applying a 1,000 Newton force. That's kind of an aside. Hey, a person pulls a toboggan for a distance of 35 meters along the snow with a rope that is directed 25 degrees above the snow. The tension in the rope is 94 newtons. How much work is done on the toboggan by the tension force? Work equals force times distance times cosine theta. So the force of 94 newtons times the distance of 35 meters times cosine of 25 degrees, 25 cosine, I'm getting 2,982 joules of work is being done by the tension force in the rope, and the rope is angled 25 degrees above the snow. If instead the person pulls way down parallel to the snow, like right where it's attached to the toboggan, then it's just 35 meters times 94 newtons, 3,290 joules of work would be done if the same tension is directed parallel to the snow. All right, is work a vector quantity? Can one do positive work and negative work? Well, yes. If you're working out and you're lifting up the barbell, then you provide a positive force over a positive displacement. Work equals force times distance. You have done positive work. If, on the other hand, you bring the barbell back down, and you don't just drop it, you keep applying the positive force to bring it down at a constant velocity instead of having it accelerate down and crush your chest, well, in that case, you're doing positive force with a negative displacement. You're doing negative work. One way to think about this is a little foreshadowing. We're going to talk about gravitational potential energy. When you lift up the barbell, you increase its gravitational potential energy, mgh. The mass of the barbell times the acceleration due to gravity times the height above the ground, or above whatever you're going to call zero, that you lift it. So in the first case, when you do positive work, you're increasing the gravitational potential energy of the barbell. In the second case, where you do negative work, you are decreasing the gravitational potential energy of the barbell. Positive work and negative work. So the work energy theorem will state, so for now we have two types of energy. Kinetic energy equals 1/2 mv squared. Anything that has mass, and any mass that is moving has velocity. So it has some sort of energy. We call that linear kinetic energy or translational kinetic energy. For right now, we'll just call it kinetic energy, 1/2 mv squared. The other type of energy I just spoke about, gravitational potential energy, mgh. So at the bowling alley, the ball feeder mechanism must exert a force to push the bowling balls up a 1 meter long ramp. The ramp leads the balls to a chute 0.5 meters above the base of the ramp. Approximately how much force must be exerted on a 5 kilogram bowling ball? So what we're doing here is we're doing work on the bowling ball to change its gravitational potential energy, to give it mgh. So its mass of 5 kilograms times g, which is about 10, times h, 0.5 meters. It's about 25. 5 times 10 is 50 times 0.5. About 25 joules of energy that we're giving to this ball. And we're giving that ball 25 joules of energy over a distance of 1 meter. Work equals force times distance. So in order to do that 25 joules of work over a distance of 1 meter, we must have a force that is about 25 newtons. Answer 3 is 25 newtons here. Hey, 2 marbles, one twice as heavy as the other, are dropped to the ground from the roof of a building. Just before hitting the ground, the heavier marble has as much kinetic energy as the lighter one, twice as much kinetic energy as the lighter one, half as much kinetic energy, 4 times as much, impossible to determine. Alright, so back when we talked about gravity, it was a little perplexing that if I drop a heavy rock and a small pebble off the top of the building, they would both reach the ground at the same time. They would both have the same velocity if we ignore air resistance. So we're saying that they are both subject to the acceleration due to gravity, and that's the only thing that matters. But you know that there's a difference between having a pebble hit you from the top of the building or a big rock. So it's not the velocity that matters, it's the kinetic energy. So if one of these marbles is twice as heavy as the other, and the velocities are the same, 1/2 mv squared, velocity squared is the same value, then just before hitting the ground, the heavier marble, the only difference is that it has twice as much mass, so it must have twice as much kinetic energy. So, answer 2. Alright, water slide is constructed so that swimmers, starting from rest at the top of the slide, leave the end of the slide traveling horizontally, as the drawing shows. One person hits the water 5 meters from the end of the slide in a time of 0.5 seconds after leaving the slide. Ignoring friction and air resistance, find the height of the slide in the drawing. Okay, so here's the deal. They're going to leave the slide traveling horizontally. This is like a quiz question we had about a ball rolling off the roof of a building. If they leave the slide traveling horizontally and they travel for 5 meters in a time of 0.5 seconds, that means that they left the end of the slide traveling at 10 meters per second. Alright, well they're going to start at the top of the slide with gravitational potential energy, mgh, and they're going to leave the end of the slide with kinetic energy, 1/2 mv squared. If you notice, mass appears on both sides of the equation. So we have gh equals 1/2 v squared. We have one equation with one unknown. We just don't know the height. Height equals 1/2 v squared over g. So the velocity is 10 meters per second. 10 squared is 100 times 0.5 divided by 9.8. We get a height of 5.10 meters. That's actually the height from the top of the slide down to the bottom of the slide. If we want to find the total height, we need one other thing here, back to our time of kinematics. They left the slide traveling horizontally and fell in 0.5 seconds. That's free fall motion. So that's an initial velocity in the y-axis of 0 meters per second. Remember, they were traveling down the slide and then they left the slide traveling horizontally. They're traveling horizontally. They have some x-axis velocity that we figured out to be 10 meters per second, but their y-axis velocity right there is 0. So they start from rest on the y-axis. They have an acceleration of negative 9.8 meters per second squared. And what? And a time of 0.5 seconds. So we have our three knowns. Our two unknowns are going to be final velocity and distance. Distance is what we would like to find out. So y equals, what do I want to do here? I don't know my final velocity. So v squared, no, y equals v naught t plus 1/2 at squared. There's the one. So y equals v naught t plus 1/2 at squared. The initial velocity was 0, so that's easy. So y equals 1/2 at squared. 1/2 times 9.8 meters per second squared times 0.5 squared gives me 1.23 meters. So the total height is going to be the 5.1 meters that I figured out from the top of the slide to the bottom of the slide, plus 1.23 meters will give me 6.33 meters for the total height that they gave us here, the total height of the water slide. Alright, that was an overview of work and energy. There's a lot more to it, but I think you get all that figured out in the homework. Enjoy!